We are going to demonstrate the effectiveness of our ceramic and cork coatings at preventing the transmission of energy. In this case, we're going to be using dry ice and placing a sample on top of each of the bowls once filled with dry ice. We have 3 samples. The black sample is blank. It's simply a piece of metal. This sample in the middle, the green sample, has our Reve cork coating, and the white sample is coated with ceramic extreme. Each bowl is filled with a little bit of water at the bottom to help transfer the energy from the dry ice into the bowl or the cold. We'll fill each bowl up and then place the samples with the coated side facing down on each of the metal bowls. You can see the vapors coming off the dry ice because it is so cold. It sits around negative 40 degrees Fahrenheit. Alright, now we have our bowls filled. We will place each of the samples coating side down on top of the piles of dry ice. Right now we are starting this at about 2:05, and we'll take measurements at 5 minutes and then again at 10. So we'd expect the blank sample to cool down extremely fast. With the dry ice being so much colder than the room, there's really nothing stopping that piece of metal from cooling down. Our first measurement, less than a minute in, is around 35 degrees Fahrenheit and falling. The cork coating is around 58 degrees, and then the ceramic coating is around 55 degrees. So already we have about a 20-degree difference between the uncoated and coated samples. Now we take the measurement when we first start, again at 5 minutes and then again at 10 minutes, because we want to see how well the coatings actually sustain the cold or prevent the cold from transmitting into the metal over a period of time, not just instantly. Because when we apply both of these coatings to the inside and the outside of buildings, they're not exposed to cold or heat for just a moment or two. It lasts all day long. So we want to get to a place in this test where each of the samples has been exposed for a period long enough where the entire sample, the bowl itself, and all of the dry ice has had time to take full effect. Both the Reve cork and ceramic extreme can be applied to walls and roofs. They're incredibly effective at preventing energy loss in the form of overheating in the summer or cooling in the winter. So it's been a couple of minutes since we first started. We'll take another reading. The uncoated sample is already at -7, -8 degrees Fahrenheit. Our cork sample is still at 55 degrees Fahrenheit, and then the ceramic is at 50 degrees. So right now we're seeing temperature differences between 55 degrees and 60 degrees Fahrenheit. For reference, the temperature of the dry ice is still around -40 degrees Fahrenheit. We can see here that the side of the uncoated sample facing the room has started to have some condensation form on the top, and the condensation is refreezing because that dry ice is so cold. The other two samples, both the cork and the ceramic, do not show any signs of condensation because they are slowing the transfer of that cold into the metal plate. A little hard to see here, but we're showing the uncoated metal plate around -30 degrees Fahrenheit. The cork-coated sample is at 50 degrees Fahrenheit, and then the ceramic is around 43 degrees Fahrenheit. Right now we have an 80-degree differential between the uncoated sample and our cork, and a 70-degree difference for our ceramic coated sample. Okay, so we've jumped ahead to the 10-minute mark. The uncoated sample sits below 40 degrees Fahrenheit. Next, our cork-coated sample is at 39 degrees Fahrenheit. Still about an 80-degree difference from our initial reading. Depending on the exact location that we measure on the uncoated sample, we may get temperatures warmer or cooler because of the contact with the dry ice. But the results from the coated samples are just incredible. Over 70-degree differential for the cork and over 60 for the ceramic coated. Those two coatings have literally stopped the transfer of cold into these metal samples. You can see all the bowls have condensated, and the condensation has refroze on the outside due to the ambient temperature and humidity of the room. And on the flip side, the two coated samples have actually kept the dry ice in those bowls from melting as quickly as the dry ice is in the bowl with the blank metal sheet on top. So it works both ways with the transfer of heat. Number one, it has protected the metal from becoming super cold like our control sample, but also number two, it's protected the dry ice from melting from exposure to the warmer air in the room. So in this spot on the plate, we're below 40 degrees Fahrenheit again, or negative 40 degrees Fahrenheit rather. We're at 35 on the cork coated and 20 degrees Fahrenheit for the ceramic. And even though the thickness of the ceramic and the cork is very small compared to traditional insulation, the temperature differential over a sustained period of time has continued to perform. It's incredible to see a 60-degree plus difference in these thin coatings when applied to dry ice. And we can see the bottom side of that control sample was clean of condensation because it was continually exposed to the dry ice. And then when we measured the temperature of the dry ice to finish off, we can see that the coated samples actually protected it from warming up compared to the control sample, which is exposed only to the metal sheet and allowed the ambient temperature of the room to warm up that dry ice.